In what follows, we discuss descriptive analytics. Descriptive analytics is also referred to as unsupervised learning, since there is no target variable available to steer the learning process. The idea is to find structure in an unlabeled dataset. Common techniques are clustering, association rules, and sequence rules. We discuss these into more detail in what follows. Clustering is a first descriptive analytics activity. The aim here is to group a dataset of observations into clusters or segments so that the homogeneity within a cluster is maximized and the heterogeneity between clusters is maximized. In other words, segments should be cohesive and well separated from each other. The discovered segments can then be individually approached using tailored strategies and policies. Some example business applications of clustering are the following: improving the understanding of the customer population for targeted marketing or advertising, efficiently allocating marketing resources or budget and doing mass customization, differentiating between brands in a portfolio, identifying the most profitable customers, clustering claims in an insurance setting, and clustering cash transfers in an anti-money laundering setting. When used for fraud detection, a possible aim of clustering may be to group anomalies into small, sparse clusters. As you can see in the figure, the three red observations make up a separate small cluster in terms of the recency and frequency. These could then be labeled as anomalies and be further analyzed and inspected in terms of their characteristics and potentially fraudulent behavior. Various data characteristics can be used for clustering. A first set of characteristics are demographic characteristics such as age, gender, income, education, marital status, and children. Examples of lifestyle characteristics are vehicle ownership, internet use, travel, pets, and hobbies. Also, attitudinal information can be interesting to analyze, such as product preferences, price sensitivity, and willingness to try other brands. Behavior characteristics characterize the customer behavior. Examples are products bought, prices paid, use of cash or credit, and the well-known RFM variables. RFM represents recency, frequency, and monetary, and are very popular in marketing and fraud applications. Remember, recency refers to the recency of the most recent transaction, frequency to the frequency of transactions, and monetary to the monetary value of a transaction. The RFM variables can be operationalized in various ways. As an example, the monetary variable can be operationalized by looking at the average, maximum, minimum, or most recent amount of a transaction. Acquisitional information, such as marketing channel and promotion type, can be handy for clustering. Finally, social network information can also be included, such as the purchase behavior of your friends, socio-demographic characteristics of friends, and so on. Different types of clustering have been developed in the literature. At a high level, clustering methods can be categorized as either hierarchical or non-hierarchical. Hierarchical methods seek to build a hierarchy of clusters, whereas non-hierarchical methods typically cluster observations into a predetermined number of clusters using an iterative procedure. Popular examples of hierarchical algorithms are agglomerative and divisive algorithms. Popular examples of non-hierarchical algorithms are k-means clustering and self-organizing maps or SOMs. In what follows, we discuss agglomerative, divisive, and k-means clustering. SOMs are discussed in more advanced courses on analytics. Here, both divisive and agglomerative clustering are explained. The two most extreme clustering solutions are depicted to the left, where all observations are put into their individual cluster, and to the right, where all observations are put into one big large cluster. Agglomerative methods start from the left and move to the right, by each step merging observations and or clusters. Divisive methods start from the right and move to the left by each time splitting clusters into smaller parts. The optimal clustering solution is then situated in between. As already mentioned, clustering aims at grouping observations based on similarity. In order to do so, a similarity measure needs to be adopted. Various similarity or distance measures have been introduced in the literature. Let's consider two observations characterized in terms of their recency and monetary values. Observation 1 has a monetary value of 30 and a recency value of 10. Observation 2 has a monetary value of 50 and a recency value of 20. A first way to measure the similarity is by calculating the Euclidean distance. This equals the square root of 50 minus 30 squared plus 20 minus 10 squared, or 22. Another measure is the Manhattan or city block distance, which is named after the street pattern of New York. This is calculated as 50 minus 30, the absolute value thereof, plus 20 minus 10, the absolute value thereof, or 30. Obviously, the Manhattan distance is bigger than the Euclidean distance. We have already discussed how to measure the distance between individual observations. A related question now is how to measure the distance between clusters. Various options are available here. In the single linkage method, the distance between two clusters is defined as the shortest possible distance between any two members or observations in both clusters. The complete linkage method defines the distance between two clusters as the maximum possible distance between any two members or observations in both clusters. The average linkage method calculates the average distance between all members or observations in both clusters, whereas the centroid method calculates the distance between both cluster centroids. In order to decide upon the optimal number of clusters, a dendrogram can be used. This is a tree-like diagram that records the sequences of merges. Let's illustrate this with an example. Assume that we want to cluster birds in terms of their characteristics, such as the way they look, the noise they make, what they eat, and where they live. You can see the clustering process illustrated here. First, we group chicken and duck, then parrot and canary. Step 3 adds pigeon to the chicken and duck cluster. Step 4 clusters owl and eagle. Step 5 merges the clusters obtained in step 2 and 3, and step 6 merges everything together. An obvious question is, where should we stop clustering? Here you can see the corresponding dendrogram for a bird clustering example. The vertical scale gives the distance between two clusters merged. The dendrogram can then be cut at the desired level to find the optimal clustering. The red line indicates our optimal clustering. In other words, there are three clusters. Cluster 1 has chicken, duck, and pigeon and can be labeled as poultry. Cluster 2 has parrot and canary and can be labeled as exotic birds. Cluster 3 has owl and eagle and can be labeled as predators. Note that good labeling of the clusters is very important to facilitate the interpretation thereof. It is typically done by close collaboration between the data scientist and business user. K-means clustering is a very popular non-hierarchical clustering method. It starts by selecting K observations, which will serve as our initial cluster centroids or seeds. Each observation is then assigned to the cluster that has the closest centroid, for example in Euclidean sense. When all observations are assigned, the positions of the K cluster centers or centroids are recalculated. This process is repeated for a fixed number of steps or until the cluster centroids no longer change. Let's illustrate this with an example. We start from a set of observations that are described by two characteristics, for example, the recency and frequency. We will now perform k-means clustering and set k to 2, which means that we want to find two clusters. In step 1, two observations are randomly chosen as our cluster centers. They are depicted by the black circle and the red triangle, respectively. The remaining observations are now assigned to both cluster centers by calculating the Euclidean distance. This results in the black and red cluster. In step 2, the cluster centers are recalculated. They are again depicted by the black circle and red triangle. Here you can see all observations reassigned based on the new cluster centers. In step 3, the new cluster centers are calculated. Here you can see the observations reassigned. This is where the k-means clustering ends and results in the black and red clusters. Association rules are a second type of descriptive analytics. They aim at detecting frequently occurring patterns or relationships between items. Again, as I said, this is an example of descriptive analytics or unsupervised learning, whereby there's no real target or dependent variable for which to optimize. The first example is market basket analysis, whereby the goal is to analyze which products or services are frequently bought together. This information can then be used for product bundling or shelf organization. Another example is analyzing which web pages are frequently visited together. This can be useful for optimizing website design. It can also be used for text analytics to study which terms frequently co-occur in a text document. This can then be used by text summarization tools. Finally, associations between course electives can be used to optimize university timetabling. Association rules typically start from a database D of transactions TP, or transactions T. Every transaction has a transaction identifier and a set of items that are selected from all possible items. In a market basket analysis context, the transaction idea is a purchase idea and the items are the products that were purchased. In a web analytics context, the transaction idea is the visit idea and the items are the web pages that were visited. In a text analytics context, the transaction idea is a document idea and the items are the words in the document. In a university timetabling context, the transaction idea is a student idea and the items are the electives chosen by the student. An association rule is then an implication of the form X implies I, where both X and Y are a subset of all possible items I. The intersection between X and Y is empty. X is often referred to as the rule antecedent and Y the rule consequent. Some examples are as follows. If a customer has a car loan and car insurance, then the customer has a checking account in 80% of the cases. If a customer buys spaghetti, then a customer buys red wine in 70% of the cases. Here you can see an example of a transactions database in a market basket analysis setting. For example, in transaction 1, the items beer, milk, diapers, and baby food were purchased. Obviously, not every transaction should have the same amount of items. It is very important to be aware of the fact that association rules are statistical rules in the sense that they are typically only true in a majority of the cases. Hence, measures are needed to quantify the strength of the association. Two key measures are the support and the confidence. The support of an item set is the percentage of total transactions in the database that contains the item set, or the rule X implies Y has support S if 100 times S% of the transactions in D contain X union Y. It can be calculated by dividing the number of transactions that support X and Y by the total number of transactions. A frequent item set is then an item set for which its support is higher than a pre-specified threshold, which is referred to as min sub. The association rule X implies Y has confidence C if 100 times C% of the transactions in D that contain X also contain Y. In other words, the confidence is the conditional probability of the rule consequent Y given the rule antecedent X. It can be calculated as the support of X and Y divided by the support of X. Let's illustrate a calculation of the support and confidence with an example. Here you can see the transactions database we introduced earlier. Let's now consider the item set baby food, diapers, and beer. The item set occurs in the red transactions 1, 6, and 9, giving a support of 3 out of 10 or 30%. Based on this item set, various association rules can now be derived. Let's pick one as an example. Baby food and diapers imply beer. To calculate the confidence of this association rule, we first need to calculate the support of baby food and diapers. This item set occurs in 5 transactions, which are underlined. More specifically, transactions 1, 3, 6, 8, and 9. Out of these 5 transactions, 3 also include beer, giving a confidence of 3 out of 5, or 60%. Mining association rules from data is essentially a two-step process as follows. In the first step, identification of all item sets having support above min sub, in other words, the frequent item set, and in the second step, discovery of all derived association rules having confidence above the minimum confidence or min conf. As said, both min sub and min conf need to be specified beforehand by the data analyst or data scientist. The first step is typically performed using the a priori algorithm. The a priori property states that every subset of a frequent item set is frequent as well, or conversely, every superset of an infrequent item set is infrequent. This implies that candidate item sets with k items can be found by pairwise joining frequent item sets with k-1 items and deleting those sets that have infrequent subsets. Thanks to this property, the number of candidate subsets to be evaluated can be decreased, which will substantially improve the performance of the algorithm since less database passes will be required. The a priori algorithm is illustrated here. We start from a database with 4 transactions, with transaction identifiers 100, 200, 300, and 400. Suppose we set the minimum support to 50%. We then find 4 frequent item sets with 1 item as listed in table L1. These are the item sets with items 1, 2, 3, and 5. We then consider all item sets with 2 items by pairwise merging the frequent item sets of size 1. This gives us the item sets listed in table C2. For each of them, we count the support. This gives us 4 frequent item sets of size 2 as shown in table L2. We continue this reasoning. However, we make sure to apply the a priori property. For example, let's say we merge item sets 1, 3 and 2, 3 to 1, 2, 3. We already know that this can never give us a frequent item set, since the item set 1, 2 is not frequent, hence we don't have to consider it. By applying the a priori property, there's only one candidate item set of size 3 that remains to be considered, and that is the one with the items 2, 3, and 5. We can then count its support and indeed find that it is a frequent item set. The resulting frequent item sets are listed at the bottom of my slide. Once the frequent item sets have been found, the association rules can be generated in a straightforward way as follows. For each frequent item set K, generate all non-empty subsets of K. Secondly, for every non-empty subset S of K, output the rule S implies K minus S if the confidence is above the minimum threshold, min conf. Note that the confidence can be easily computed using the support values that were obtained during the frequent item set mining process. For the frequent item set baby food, diapers, beer, the following association rules can be derived. Diapers and baby food implies baby food. Diapers and beer imply baby food with confidence 75%. Baby food and beer implies diapers with confidence 75%. Baby food and diapers implies beer with confidence 60%. Beer implies baby food and diapers with confidence 50%. Baby food implies diapers and beer with confidence 43%. And finally, diapers implies baby food and beer with confidence of 43%. If the minimum confidence is set to 70%, only the first two association rules will be kept for further analysis. Given the above example from a supermarket transactions database, where we look at the purchases of coffee and tea. Let's now consider the association rule tea implies coffee. The support of this rule is 100 divided by 1000 or 10%. The confidence of the rule is 150 divided by 200 or 75%. At first sight, this association rule seems very appealing given its high confidence. However, closer inspection reveals that the prior probability of buying coffee equals 900 divided by 1000 or 90%. Hence, a customer who buys tea is less likely to buy coffee than a customer about whom we have no information. The lift, also referred to as the interestingness measure, takes this into account by incorporating the prior probability of the rule consequent as follows: support x union y divided by support of x times support of y. A lift value less than 1 indicates a negative dependence or substitution effect, whereas a lift value of bigger than 1 indicates a positive dependence or complementary effect. In our example, the lift value equals 0.89, which clearly indicates the expected substitution effect between coffee and tea. Typically, an association rule modeling exercise will yield lots of association rules, so post-processing will become a key activity. Example steps that can be considered here are: filter out the trivial rules that contain already known patterns, such as buying spaghetti and spaghetti sauce together. This should be done in close collaboration with a business expert. Perform a sensitivity analysis by varying the minimum support and minimum confidence values. Particularly for rare but profitable items such as Rolex watches, it could be interesting to lower the minimum support value and find the interesting associations. Use appropriate visualizations such as OLAP-based facilities to find the unexpected rules that might represent novel and actionable behavior in the data. And finally, measure the economic impact such as profit or cost of the association rules. Association rules can be used in various ways. As said, in a market basket analysis context, they can be used to detect which products or services are frequently bought together. Obviously, this has important implications for targeted marketing, such as deciding on the next best offer, product bundling, store layout, shelf organization, and catalog design. When combined with customer loyalty card and RFID data, for example, in a supermarket context, association rules provide a very powerful technique to disentangle complex customer shopping behavior. Let's assume we have an association rule: baby food and diapers implies beer. What can we do with this information? Well, we can put them together to make sure that they are always purchased jointly. Another option is to put them far apart so that customers may purchase additional items in between. We can package all three items and maybe add a poorly selling item to it. We can see what happens when we raise the price on one and lower it on the other. There's no need to advertise all three together since they are already purchased anyway. As you can see, there are plenty of marketing actions which we can do based on this information. Association rules can also be used to build recommender systems that help people make decisions based on preferences. Recommender systems are used in e-business to recommend items, in e-learning to recommend courses, and in search and navigation to recommend links. They are commonly used by companies such as Amazon, eBay, and Netflix. Here you can see an example of my database management book on Amazon. This is the book that we also use in the course Principles of Database Management. You can see that Amazon detected a significant association between users that viewed my database management book and three other books, two of which I also co-authored myself. Let's now discuss sequence rules as a third type of descriptive analytics or unsupervised learning. Given a database D of customer transactions, the goal of mining sequence rules is to find the maximal sequences among all sequences that have certain user-specified minimum support and confidence. Important to note here is that contrary to association rules that work with sets, the order of the items in a sequence is important. An example could be a sequence of web page visits in a web analytics setting: home, electronics, cameras and camcorders, digital cameras, shopping cart, order confirmation, and then return to shopping. Transaction time or sequence field will now be included in the analysis. While association rules are concerned with what items appear together at the same time or intra-transaction patterns, sequence rules are concerned about what items appear at different times or inter-transaction patterns. Consider this example of a transactions dataset in a web analytics setting. The letters A, B, C refer to web pages and the sessions to web visits. A sequential version can then be obtained as shown to the right. We can now calculate the support and confidence as with association rules. Consider the sequence A implies C, or A to C. One can now calculate the support in two possible ways. One approach would be to calculate the support whereby the consequent can appear in any subsequent stage of the sequence. Here, the support becomes 2 divided by 5, or 40%. Another approach would be to consider only sessions where the consequent appears right after the antecedent. Here, the support becomes 1 divided by 5, or 20%. A similar reasoning can now be followed for the confidence, which can be either 2 divided by 4, 50%, or 1 divided by 4, 25%, respectively. Sequence rules can be used for customer journey analysis. A customer journey is a diagram representing the various steps that customers go through when engaging with a firm. The idea here is to start from an event log of activities as depicted in the table below. The event log depicts a unique customer identifier, the various activity names, and their timestamps. Here you can see an example of a resulting customer journey. Customer journey analysis serves various business purposes. It can be used to get a clear and comprehensive picture of the overall process and highlight process deficiencies such as excessive processing times, deadlock situations, circular references, and unwanted customer leakage, amongst others. It can also be used to verify if the process is compliant with both internal and external regulations. If you want more information about any of these topics, I'm happy to refer you to any of my books listed here and which are available on Amazon.com.